Okay, so let's talk about Newton's first law. You may know it as from middle school or from when you were younger as an object in motion tends to stay in motion, an object in rest tends to stay at rest. That may not have meant much to you though, because it doesn't compute with our natural understanding of the world, or at least what we perceive naturally as humans. And this was the case in history too. So human beings used to think that the natural state of things was at rest, and the natural state of that the natural state of things was to slow down, because we see things at rest, they don't move, and then if we throw some object, right, it slows down. Or if you hit a hockey puck, right, let's take an example that even further proves the old way of thinking, and then we'll dismantle it. But if you take a hockey puck, there's something I can finally draw. It's not black, I know, but bear with me. If you hit it, the hockey puck will continue going. However, even it will slow down and come to a stop if you have a large enough ice rink, right? Now, why is that? Well, it's because there are forces acting on the hockey puck after you hit it. So let's take the situation right after the hockey puck leaves the stick and it's traveling in some direction, right? Some initial velocity away, let's say it's in that direction. There are forces acting on the hockey puck. So there's the force of friction, right? The ice, although it doesn't have much friction, you may know this if you walk outside on an icy day and fall down because it's so slippery, which is the opposite of friction, kind of, how slippery something is. Even ice has friction, right? And there's also air resistance. So we know that the hockey puck will slow down eventually. So you might say, Mr. Woodard, the old way of thinking was correct. Even the hockey puck slows down eventually and stops. However, space has totally thrown this idea out the window, because we know if you launch an object in outer space, in a vacuum, right, where there's no air resistance to slow it down, if you launch an object in outer space, it will continue going forever at that speed. It will only speed up. It will only speed up if you push it harder, and it will only slow down if you push it in the direction that opposes the direction it's currently traveling, right? So Newton was right. This is true. An object's motion will only be changed by a net force. Now, what does the net part of that mean? Well, let's take a different example. Let's take a car. I'm going to draw the car like a hockey puck because that's all I can draw. So here's a car, but now it has wheels. All right. We can get a car going at a constant velocity, v0, right? It can be traveling at a constant velocity, v0, and there are forces acting on it, all right? The only thing is the net force acting on a car going at a constant velocity is 0. So net force equals 0 at constant velocity. That's the net force. That doesn't mean there are no forces, okay? There is a force pushing the car forward, right? Sorry, I don't know why it's doing that. My pen's being a little different today. Okay, I'll just try to draw a dot here. There's a force pushing the car forward, and there's a force pushing the car backwards, right? And pretend those are straight lines because I'm doing my best. Sorry, I switched to OneNote 2016, so it's not cooperating as well. I might switch back. But these forces are opposing each other, right? And if they cancel out, it's almost like there's no force acting on the car, but it's not the case. There are forces acting on the car. The force that's pushing the car this direction is the engine, right? Or it's the force of torque from the wheels ultimately down here. But there's a force pushing the car that direction. The force that's pushing it this direction is friction and air resistance, and they cancel each other out. And the only way to make the car go faster is to increase that force. The only way to make the car go slower is to increase the force that opposes the direction. If these forces remain constant and the net force is 0, it will travel indefinitely at the velocity that it started with. Okay, so let's look at Newton's second law. So this kind of leads to Newton's second law, and these will complement each other well, I think. So Newton's second law is mathematical, and it says that the sum of the forces acting on an object or a system, all right, you could have a system of objects, the sum of the forces acting on a system are equal to the system's mass times its acceleration. This is different maybe than what you saw in middle school. In middle school, you may have just seen this, F equals ma, right? And you may have been able to calculate the force, and that's great and all, but we're now moving on to this guy, right? That's sigma. This means sum, like mathematical sum. So add up all the forces. They're going to be equal to the system's mass times its acceleration. Okay. This leads us to an interesting question that I don't want to get sidetracked on, but it popped into my mind. If I ask you to define mass, by the way, which I might in a later video or in a problem set, mass we actually define with force, okay? When you weigh something, you're using the force of gravity to talk about mass, and it relates very nicely to this equation. But moving on, let's relate it to the first law here. So we said, hey, net force equals 0 at constant velocity. And we know constant velocity from kinematics means or equals acceleration of 0. Right? So if we plug in a 0 acceleration, let me add a page to this. So let's say acceleration equals 0, right? That means that the sum of the forces equals mass times 0. So the sum of the forces must be equal to 0. So that's kind of where the first law comes from, or the second law is an expansion on it, right? If I want to find the acceleration on an object, I can rearrange it and say the sum of the forces divided by the object's mass is equal to its acceleration, right? Now, what this means, and we saw this in class a little bit, is the more massive an object is, if you increase m, a will go down. They're inversely proportional. So if we say the sum of the forces on an object, let's say it's a bike. Can I draw a bike? It looks like a cylinder. It's not a great bike. I don't know. That's all right. It could be better. Here's the bike seat. Okay. It's doing that thing again. Here we go. Here's the bike seat. Okay. If we have a bike and we have two net forces that are acting on it, right? The force from your legs and then the force of friction and air resistance going on it. Let's say that your legs are pushing on the bike pedals harder so that the force pushing you this way, right? Let me get my... You guys are seeing me battle the laptop today. Okay. Let's assume that the force going this way is bigger than the force going this way, right? That means that the sum of our forces, if we add these together, we'll have a net force. It's kind of this way, right? Not quite as big as this one here, but you know, we're still going to go this way. So we have a net force. Divide by the system's mass, so your mass and the bicycle, right? So the mass of the person on the bicycle and the bicycle gives you the acceleration here. Okay, now let's assume the same net force down here, the same net force is applied to a train. All right, here's how I draw a train, right? It's the hockey puck with this, all right? There, now it's a train. Okay, the same net force is applied to a train car. Now, the acceleration will be much, much smaller, right? Because mass of the bicycle is way, way smaller than the mass of a train car. TC for train car. Which means that the sum of the forces, right, divided by the mass of a bicycle is going to be a number, which is the acceleration of the bicycle. If we're dividing by a very small number, the acceleration should be higher, right? And same thing, I'll put it here. the sum of the forces over the mass of the train car, right, will equal the acceleration of the train car. And we know that if this number down here gets really big in the denominator, if you're dividing by a very large number, then the acceleration should be smaller. Okay, so this is Newton's first and second law. And something that I need to touch on is that as far as we're concerned, constant velocity and being at rest are indistinguishable from each other. Right? It just depends on your frame of reference. So we'll do a new page to add some frame of reference stuff here. So let's assume that you're traveling in a train, right? There's two frames of reference we could think about. I know my train kind of got crooked there at the bottom. There's two frames of reference we could think about. We could look out here at the train car moving, right, at constant velocity. That's a frame of reference. Or we could look inside the train car and we could be moving with the train car. Okay? As far as we're concerned, though, the objects in the train car don't know if they're at rest or if they're moving, right? And we know this is intuitive to us. If we're sitting on an airplane or we're sitting in a train car moving at a constant speed, we forget that we're moving, right? I mean, right now, we're currently moving on the Earth. So we don't feel velocity. And well, we don't feel constant velocity. We feel changes in velocity, which we'll keep touching on more. But what I want you to know is that as far as Newton's first law is concerned, being at rest and being at constant velocity are the same. Okay? It's about changing velocity. That is when we're dealing with there must be a net force acting on your system. Okay. I will see you in the next video. Hopefully I haven't rambled too long.